Hi, my name is Jan Wichelmann from the University of Lübeck, and I'm presenting our work Obelix, which is a software drop-in countermeasure against lots of different side channel classes through a dynamic obfuscation engine. So yeah, let's get started with the background. So trust execution environments, or TEs in short, are used for protecting workloads running on some untrusted location. So for example, we have our program, which is a piece of code consisting of a number of instructions, for example, a recipe for a secret strength potion. Then we have a computation, which is some processor or kettle with the ingredients in there, the potion. And we have memory where some secret data is. So for example, our ingredients which we use for our potion. And we are running this program or brewing this potion in some untrusted location, for example, on a third-party cloud machine or some potion brewing competition. And we don't want anyone else than us to see what we are doing. So we don't want someone to steal a program or secret algorithm or secret potion recipe, and no one should learn what our secret data is. And to enable that, processor vendors have introduced these TEs, which add a hardware-enforced isolation layer around our process and keep privileged attackers, so the cloud provider, for example, who has full access to the machines, from tampering with our data or extracting our data. And they achieve that through memory encryption, for example. So the entire memory of our virtual machine, for example, is encrypted. The privileged attacker cannot access our data or our code and can modify it. And they have remote attestation, so we can verify that our workload in the cloud is actually the program which we send to the cloud provider and not something different before we send our secrets there. Okay, so this is nice, right? Encryption is great, so it should be secure. Well, it's not, of course. There are side channel attacks, unfortunately. So to illustrate that, I've prepared a very short program, a very short recipe, which consists of 6 instructions. 2 of them are memory accesses. And yeah, let's look at memory accesses. So we have the first access to ingredient A. And well, we can't see where it is because memory is encrypted. However, we can see where the access goes. And we see that we access the memory page shelf 1, where there are like 2 different ingredients. So we can infer we access either this one or this one. And so the attacker learns something about the accessed ingredient, even though they cannot read the memory itself. The same is for the other one, where we access a different memory location. The attacker still sees which location is accessed, so they can build a memory access pattern. And this pattern allows reconstructing, for example, accesses to some lookup tables, which allow breaking keys, which has been used, for example, by many cache attacks and TLB attacks. This is pretty bad already, but it gets worse. TEs are very special in that they have a very strong attacker model. And the attacker model also allows to interrupt the TE. And, well, right now it's pretty fast, so the attacker can't really distinguish single instructions. However, they can program a timer to interrupt the TE after every single instruction. So they step the program, as the name says, instruction by instruction. So they can run this one, measure its latency, for example, so they can very precise measurements on top. They can very precisely measure the memory access, and so on, and so on, and so on. So they step through the program and can count instructions. So how does it look? Well, so there's memory encryption, there's access prevention. However, there are tons of side channels. So TEs are not really trusted anymore. And are we doomed? There's no security here, or can we somehow fix that? And well, there are countermeasures actually for TEs. So some of them, unfortunately they only fix one issue. So there's one for single stepping, another one for cache attacks. For example, constant time code is very robust against memory access pattern attacks. However, you have to know how to write constant time code, and it's very manual and error prone. So not really something for the average user. There are some hardware countermeasures, but they are all for single attack class and not really compatible, and there's no thing that just solves all issues. And so we wondered, how many side channels can we fix with a single software drop-in solution? Okay, so let's get started with the simplest one. Memory access leakage. A very simple solution to that is oblivious RAM or ORAM. So you may wonder, alright, ORAM, that's slow. Well, wait for a minute, I will talk about it later. So what's the issue? So we know which location memory we are accessing. What about if we, for every access, just access every memory location and use some magic constant time selection primitive, which then magically picks the right data from the red one. So we read all data and just select the one which we are interested in via some masking scheme. This way the attacker sees always the same access pattern because we access everything each time. And well, yeah, memory access is secure now. All right, so what about the single stepping issue? So what about the code? So that's a bit more difficult. So let's get back to the example. So we have 4 instructions on the first page and 2 instructions on the second page. And I have a look at the measurements from single stepping. We can measure the latency of instructions and well, even if the colors weren't there, you will see, well, okay, we can directly see the pattern. We see the first 2 instructions, the blue ones, recite spell, are very quick. Then there is a slow memory access, then a somewhat faster stirring instruction, then again a very fast spell, and again a slow memory access. So, well, we can count the instructions, we can get their type by the latency, and we also see where the memory accesses are. So basically, we get the entire program structure, which is pretty bad if our goal was protecting our program. So we can extract the private algorithm, or we can learn the secret recipe, at least big parts of that. Okay, so how can we address that? So the issue is that there's a unique latency pattern of our program. How can we turn the program into a fixed uniform latency pattern that always looks the same? Okay, let's get started. So we define a uniform code pattern, which always consists of the same 3 instructions in the same order. And now we transform our program in a way that it always follows this pattern. So let's get started. So the first one is reset spell. We have that. Then the original program has reset spell 2, which isn't in the pattern. So we have to insert dummy instructions to fill the pattern. So we insert a dummy access to some ingredients, so a dummy memory access, which accesses something which we just throw away, so which we don't care for. Then we have a dummy steering instruction, which also does nothing, like steering without a spoon, for example, or in computation, arithmetic, where we add a 0 or something like that. All right. Then next block, this fits well. We can get page 1 done by inserting reset cell 2, ingredient A, and stirring. Then we have the first page complete, and then we translate the second page, the same as that, recite spell, ingredient B, and then we have another dummy instruction which does nothing. And our program is translated. And if we now look at the latency patterns, we see that no matter where we are in the program, we always have the same latency pattern with our block version. So right now, the attacker doesn't learn anything about the block which is executed, which isn't entirely true because the blocks have to be stored somewhere, so the attacker can still mount a memory access pattern attack against the blocks themselves, so they know which block is executed right now. And if there are loops, for example, and blocks repeat, or there are branches where blocks are skipped, the attacker may still learn something about the program control flow structure. So we have to protect that as well, but we have a solution for that already, which is oblivious RAM. So let's just put those code blocks into an ORAM as well, and yeah, have our data ORAM which we already created. So we have 2 ORAMs, and when we want to run our program, we pull the current instruction from the code ORAM into a code scratchpad, which is near our computation, and contains the code which is executed. And when we access something, we pull that data from the data ORM and put it into data scratchpad. Here we have a dummy access. We read some dummy data and write it back again afterward. Then we do next instruction and our block is done. So we can now pull the next block, execute the first instruction. Then we have a memory access where we get this memory item from the data ORM, we read it in this oblivious fashion. Then we update it. So we may change the value and write it back afterward. Because, well, there's a copy in the data ORM, so we also have to update that always. Alright, so this way the attacker always sees the same instruction latency pattern, the same instruction counts, and they don't know which block is executed, they don't know which data is accessed, so we are really secure. So we have now prevented single stepping, we have prevented memory access pattern attacks, and I didn't show this here, but in the paper, we also prevented ciphertext side channels, which is a very TE specific and strong attack, by adding some masking to the scratchpad and the code and data scratchpads, which would also prevent this attack. So to answer this question, how many side channels can we fix with a single software drop-in solution? The answer is a lot, actually. And it's also possible to extend Obelix to also fix side channels like transient execution attacks, for example, Spectre, and fault injections like Rowhammer, through some minor extensions like adding some hashing and fences at some points. So it's very, very broad what is possible here. Going back to this, you will wonder, well, yeah, of course, what is the overhead of this thing? Because ORM bad. Well, yeah, you're somewhat right. So for big programs, this doesn't scale at all because the ORMs get very big and very slow. However, for very small programs or programs where you don't really care about the responsiveness of that. So if you say, okay, let it take 100 times the execution time, but if it's only like 1 millisecond and it's asynchronous, I don't care how long it takes. And in this case, the security guarantees may outweigh the performance impact. So for slow workloads, it may be a viable solution, especially if there's more research into better ORMs, because right now we're using a linear ORM, which is very inefficient, and there may be better schemes out there which give us better complexity for accesses without compromising on security. So that's an open question right now. Yeah, so to summarize, Obelix is an obfuscation engine which hides both control and data flows through oblivious execution. It can be applied to any program via compiler extension. So we wrote an LLVM compiler extension which can just take a program, compile it in a secure fashion. So you don't need to have any expert knowledge on how to harden programs. Right now we harden against some of the most important side channel classes like single stepping, memory access pattern attacks like cache attacks, and ciphertext side channels. And we also have very easy support for more attacks like transient execution attacks and fault injections like Rowhammer. So we cover almost all relevant side channels for TEs with this countermeasure. So yeah, check out our code if you want. It's on GitHub. There's the compiler extension and our example targets. And take a look at our paper. Thank you.